objective of this video is to explain flexure torsional buckling, flexure torsional buckling check. Now onwards we are using FTB. It means that flexure torsional buckling. Second step, we going to check FTB check, and steps involved in solving the FTB problems. Now, flexure torsional buckling. What is flexure torsional buckling? Now, trying to bend about the x-axis, we bend the steel beams about the x-axis, but it twists and buckle about y-axis and buckle along the entire length. What does it mean? So I am going to explain it in the pictures. In the pictures here, I have a beam here. What is trying to do? We have a loading on this dash line. Let's say we have a loading coming on to this beam on these directions, and what happened in that conditions, it try to twist. You can see that try to twist because we are trying to bend about the x-axis, but it try to buckle about the y-axis. So it's in the entire length and it try to twist. So this kind of behavior we call flexure torsional buckling. So in one scenario we can say deflection laterally. So laterally means this is the lateral deflections. As you can see, this is longitudinal deflection and this one is lateral deflection. So this lateral deflection is happen. Twisting also occur. As you can see, it's a beam twist and buckle along the entire length. If I draw the plan view of this one, you can see this whole length buckle in that fashion. So that's what the characteristic of flexure torsional buckling. Now, how we can prevent that? There are some important points that we're going to discuss now. Now, in reality, we don't want this flexure torsional buckling to be happen. So what happened? We use the purlins and fly bracings to stop that flexure torsional buckling. I have a picture here about the purlins. So if I have a this beam here, now this beam has these purlins. Now these purlins try to stop this beam to buckle laterally. So therefore we use those purlins to stop the flexure torsional buckling. I have another pictures here in the 3D view. So if you are considering this scenario here, as you can see, these are the rafters, these are the columns, and in that rafters you can find those purlins. So these are the purlins that prevent the rafter to laterally buckle. So we also have a fly braces. I can show it that fly braces here in the another examples to prevent that buckling. So if you have a steel beam here, we have a fly bracing to stop this beam to laterally buckle. We also have these purlins to stop this beam to not buckle. Now if you have a floor like a slab and then the beam sitting onto the floor or under the floor, then we can say the beam is fully laterally supported. The FTB will not occur in that case. Now I section is open sections and it has very low stiffness compared to the circular hollow sections. What happen in the circular sections? These try to bend. If I have a loading coming here, it try to bend, but these cross sections here would not deform locally. In that case, it's just stopping this. Stopping this local buckling is to stop this local buckling. But what happened in that I sections, we have this buckling happen for this wave as well, and it also have a local buckling. So that's what the difference between open circular hollow sections and the steel beam. Now, how do we know whether the flexure torsional buckling is going to occur or not? So we have an equations L over Ry less than or equal to 80 plus 50 beta m 250 over Fy. Where it is coming from? That is coming from AS4110 on page number 53. We have L over Ry 80 plus 50 beta m 250. That is if the segment is of equal flange I section. So if you have I beams, we need to use this equation to do the FTB check. Now there are other equations given for different cross sections that you can read against this equation, which it is self-explained. If you read it, you can identify each equations for which case we should use it. But in this case we are normally going to use for this course I section, so mostly we are heavily use these equations in this course. Now what is the, I like to explain this one. Length, what is this length? Length, for example, if I want to say length is nothing but length is this length. What is that length? Length is the one that is from one purlin to the next purlin. That is the length to stop this one. Ry is you can get it from the one steel tables. That's Ry is the radius of gyration for particular beam. Beta m, we covered that beta m previously. In the worst case scenario, beta m would be taken -1. Fy, we should take it from the one steel tables. Now what is the characteristic? If you increase this length, for examples, if you increase this length, then the flexural torsional buckling going to occur. So if you increase this length, meaning that this will become greater than this value, so in that case flexural torsional buckling occurs. To not happen that flexural torsional buckling, we need to satisfy this condition. So length over Ry ratio should be less than this value. If this is the case, flexural torsional buckling is not happen in the beam. But if L over R ratio is greater than 80 plus 50 beta m 250 or Fy, then the flexural torsional buckling will occur. We always conduct the check before a problem. So we always check whether L over Ry is less than 80 plus 50 beta m 250 Fy, or it is L over R greater than 80 plus 50 beta m 250 or Ry. When L over Ry is greater than, so left hand side and right hand side, if L over Ry is greater than 80 plus 50 beta m 250 Fy, then the flexural torsional buckling will occur. L over Ry, if left hand side is less than right hand side, the flexural torsional buckling will not occur. So when what does it mean? So if the flexural torsional buckling occurs, we need to calculate the design member moment capacity. And if FTB does not occur, then in that case we need to calculate design section moment capacity. Let's say moment capacity. So we have two cases. When this one FTB occur, then we have a design member moment capacity. If FTB does not occur, we need to calculate the if FTB occurs, we need to calculate design member moment capacity. FTB does not occur, we need to calculate design section moment capacity. Now I'm taking the example here to explain this one. For examples, we have given 360 UB 56.7. For example, this beam is, let's say, 360 UB 56.7, right? And let's say Ry value, which is 39, that is going to taken from the one steel tables. 360 UB 56, and Ry value for this case would be 39 millimeters. As you can see here, Ry 39 millimeters. So that's 39 millimeters. Fy 300 megapascals. That is coming from here. On the next page, on page number 15, on the one steel tables, we have a 360 UB 56, and that is flange has 300 megapascals. We have web has a 320 megapascals. We use the minimum value between these two, so 300 megapascals. In the worst case, beta m taken -1, and we're going to assume length is equal to 10,000 millimeters. So here this length is 10,000 millimeters. What is that length? Length between two purlins to prevent that fluctuate. So we substitute those value. Let's say left hand side is L over Ry. So this is L over Ry, and length is 10,000 millimeter over 39 millimeters. That's give us 256 millimeters. On right hand side, 80 plus 50 times beta m times 250 over Fy. So 80 plus 50 times -1, so 250 over 300. That's give us 30 times 250, that is given 27. So you can see 257 is greater than 27. It's not less, is less than, is greater than 27, is not less than, and left hand side is not less than right hand side, so FTB occurs. As I mentioned here in my previous steps, when L over Ry is less than 80 plus 50 beta m 250 Fy, then the FTB does not occurs. But in this case the FTB will occurs, because you can see if I have 10,000 millimeters, this distance is very large, so this beam try to do the twisting and the buckling in the length. So we should maintain this length small enough in the such that L over R ratio should be less than of these values. So that's the quick overview of use these FTB checks. And the last one is now steps involved. Once you have that check done, then you know that you need to calculate the flexure torsional bucklings. We need to use the procedure for flexure torsional buckling. So step number 1, when you do L over Ry checks, and if you have L over Ry is greater than this 80 plus 50 beta m square root Fy 250, then you follow these steps. If this one is less than whole things here, then you should not follow these ones. Then you should just calculate this 5 ms, that is section moment capacity, right? So there are in the beam there is two procedures, one for this long FTB procedures, and another one is just a section moment capacity depending on these conditions. Now L over R, always do the L over Ry checks. Once you found that L over Ry is greater than these ones, then you should follow these ones. Then finding LE effective lengths, we're going to find the moment modification factors, that's alpha m, buckling moments m0. Then step number 5, we're going to calculate slenderness reduction factors alpha s, and the last step we're going to find design member moment capacity phi mbx. Don't worry about those steps right now, it will going to make more sense when we take the examples. Thank you for listening.